Welcome back. So we had a cliffhanger on how to deal with ranked retrieval, which it's tricky, right? Because what I presented to you right now didn't have any order in it. Because if you do ranked retrieval, the problem is this: how many results do you get? You can go to a search engine, Bing for a change, and then you look at the first 10, then you keep pressing next, 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 next. At some point, you have the entire internet if you press on next a billion times, right? So how does that make any sense to compute precision in recall in a context like that? So guess how it goes. Instead of computing precision in recall as a single value, we say single precision, single recall, or F value, and so on, we are going to plot something. So I prepared two axes. One axis is the recall, and the other axis is the precision. And we are going to just put points in there based on our ranked retrieval system. So what happens now is I'm going to take the system we want to evaluate, somebody built, and we are going to run some query from the benchmark that we got from the evaluation set. And every time, one by one, we look at them, the first document, the second document, and we look at, is it precise? Is it relevant, or is it not relevant? So let's start with the first document. So Alice is using the system, and she does something you cannot actually do with a web search engine, but only the top one, first documents. So either it's relevant or it's not relevant. So we're going to look at the two cases, relevant, not relevant. So let's first assume that it's actually relevant. So then let's hypothetically ask ourselves the question, if that was it, that's the only document that is returned, and it was a Boolean system that would return that, what would be the precision and what would be the recall here? Can anybody tell me here what the precision would be for this? Yes, we have raised hands. Can you please throw the microphone over there? Thanks a lot. Almost. Oh, almost arrived. Yeah.
I think the precision would be 1 or 100%.
Yeah, the precision would be 100%. Yeah.
And the recall 0.
Why?
Because it's based on the true negatives, right? And if we don't have any negatives, we don't have any.
So you're making the assumption that there is a vast number of relevant documents. Yep. Yeah. So under this assumption, indeed, the recall would be close to 0, and the precision is 1. So where do I put it on my graph here?
On the y-axis near the top somewhere.
Like this. Right? Exactly. So this is our first point that we put here based on the first results, 100% precision and a recall that is not quite 0, but close to 0. Okay, so let's now consider the case that it was not relevant. So it's either or, right? So it could have been this, but it could have been this. So if it were not relevant, we would have a precision of 0, right? Because now none of what we look at here is actually relevant. And the recall would be this time exactly 0. Now it's not approximately 0, it's exactly 0. We didn't even get any correct documents. So you see, these are the two cases, right? Either we are here if we get something, or we are there if we don't get anything. Okay, but now I'm going to assume we got a relevant document first, right? It's the I'm feeling lucky feature that's actually working. So now let's look at the second document. So if I look at the second document, let's think about it. Let's first assume this document is relevant. So now, what precision do I have and what recall do I have? If it's relevant. Yes?
I think still the same precision.
Yeah.
Because we have
100%.
100%. And the recall, assuming that the number of total relevant documents is very much larger than 2, also close to 0.
Close to 0, but as close to 0, or yeah, go ahead.
A bit more than with only 1 document, but still very close to 0.
Yeah, so it's close to 0, but a bit more on the right, right? So I'm going to actually display it here and slightly more on the right. So there is a little bit more of recall here. Okay, yeah, perfect. What if it had been not relevance, what would have happened? Anybody? If the second one had been non-relevant. On Zoom, maybe, or any volunteer? Or do you want to answer? So maybe you can put a microphone. Yeah.
I think the precision would be 50% then.
Yeah.
And then the recall would be basically the same still because of
the same, exactly. Slightly more than 0, but the same. So we would have been there. Do you agree?
yeah.
Right? Everybody agrees with that? That's where we would have been. So there are two cases. Either it's actually relevant and then I just go, I keep the same precision but go to the right, or I go down when I didn't get it right. These are the two things that can happen. Okay, let me assume now that it was relevant, the second one. And I go for a third one that is now non-relevant. So what happens to the precision? Now the precision is, everybody, 67, right? Exactly. And the recall is unchanged. So this is what happens. When I have something that is non-relevant, I just go down like this, right? So now if I have another non-relevant document, now my precision is 50% and the recall is the same. Okay. Now I have a document that is relevant. Now the recall increases, that we already knew. When you have a relevant document, it increases the recall, but now the precision, it used to be left the same, but this is because it was at 100%, right? But if it was not at 100%, do you agree the precision increases? Here it was 50%, and now it is 60% exactly. So the precision increases. So you see the two things that happened as you go down the list of documents and keep pressing next, 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 next. Every time you have a relevant document, you go to the right and up. Every time it's not relevant, you go down vertically, right? So you see, relevant, not relevant, you go down. Relevant, bit up, relevance, a bit up, relevance to the right, relevance, not relevance, you go down. So you see, I'm only ever going to the right, I can never go back to the left. The recall can only ever increase. So the recall keeps increasing or stay the same, and then the precision fluctuates a bit, right? When I get one right, it increases. When I get one wrong, it decreases, and so on, right? So now I get non-relevant, and so on and so on. Who gets the idea, right? Who could draw that curve if I give you a concrete set of relevant, non-relevant, basically a list of zeros and ones? Okay, awesome. So this is the idea. This here is called the precision versus recall curve. This is what we build when we have a ranked retrieval system. Okay. So this is here, I just assume that we continued like that. So what's going to happen is that we just go to the right and the right and the right and the right. And the recall, anyway, we know it's going to end up at 100%, right? If you just do it forever, we are going to end up at 100%. But the question is, now it goes left to right, how high is it going to be, right? What's desirable is that we keep a high precision and don't go down too much. It will eventually go down, of course, at some point. But at the beginning, when you search, it's crucial for the first results, right? There's a bit of post-processing that people like to do on this curve. For example, they do something like this, because now it goes up and down, and we like to look at the things that decreases. So in order to get something that decreases, that is monotonous, you actually correct it like this by marking the new highs and then going to the left like this and replacing it with this. This is the curve you get, right? Who understands this? Who thinks it's possible to implement that with an electronic system, with the input, the ones and the zeros, and you can output that with an electronic device? Who thinks you cannot? Just a trick question. In fact, you cannot, because that would require knowing the future. You see this? In order to know that you are, in order to know here that you go here, you have to already know the future here. So this is something that you can only do it once you have measured everything. This is not something you can do on the fly, right? It's important for a computer scientist to know these things, right? Can you do it online in real time, or can you only do it at the end? Well, in that case, you cannot do it on real time. You can only do it once you have all of the points on the curve. For whom does that make sense? All right. So we have this curve, now it's going down. And now we can ask ourselves the question, what is the ideal system that we'd like to have, right? This is what we'd like to have. You agree, right? We want to keep getting results that are always correct. So relevant, relevant, relevant. So the ideal search engine would be like this, with a super high precision that remains very high as you click next, next, next. It's like connecting to a search engine and everything you see on your screen is just relevant to you, right? That's the dream of a web search. It might not be the actual experience, right? This is an ideal experience. Now, this is an awful search engine. Just returns garbage to you, right? Just stuff that is not relevant. Would you buy this? Well, no, I wouldn't, because you cannot use the same trick as before, because here you just don't get anything that is relevant to you. So you cannot even revert this thing. This is because now we have a ranked system. Okay, so this is what we get. And in practice, we have something, of course, in the middle. Do we have a comment on Zoom? Abhishek, maybe?
So the comment is, but you can draw backwards as soon as you measure or drop, and you can draw not the entire graph live, but a part.
Yeah, that's very clever. I'm trying to think in real time. This is under the conjecture, which might be true, that when you reach a new high, you never break the record again. It's basically under the assumption that these keep going down. I think it's correct. It would be interesting to prove it formally. As an exercise, try to prove formally that the peaks keep going down. Or maybe it's not true, right? But if it is true, then you are absolutely correct that you could do it not in real time, but kind of in real time, right? So with a bit like it's in real time, but with back corrections, right? With back tracing on the curve. Yeah, so you have a very good point. Thank you for this. And again, try to prove it formally. Yes?
You can see that the peak gets surpassed again, right? And like
Yes.
The fifth point. So
let's try to do the thought experiment. Basically, to try to find a counterexample to that. So let's imagine now, this is what you mean, right? That we keep having positive results, then it will go back.
We can see on the graph that it surpasses the peak, doesn't it? We have a peak and at the fifth point, and then we go past it again.
Yep, you're right. Yes, yes. So what you're pointing at is here that you have a peak. Sorry. You have a peak here, and then you get again past the peak. Yeah. So yes, indeed. So yeah, you see, I wasn't thinking correctly. So yes, indeed, the conjecture is not true. You can always have a newer peak, right? So the comments you made is correct in the sense that indeed you could implement a system that every time there is a peak, it redraws the curve all the way back when you break a new record. But you can never be sure that this is it. You can never be sure that in the future you will not again break a record and backtrace all the way, right? Does it make sense?
Yes.
Yep. Awesome. And thank you for reacting in real time. You see, when you're facing an audience, you just have to take into account that your brain has this way of slowing down and you cannot think straight in real time. Okay, but this is very good thinking. That's a very good way of looking at it from how to implement this thing. Okay. And now this is not answering. Okay, so this is one more thing I wanted to show you is that what people like to do also when they draw the curve the whole way, all the way to 100% of recall, and the precision might get close to zero. Of course, it's not going to be exactly zero, but goes down. What people do is that they like to take it every 0.1, 10%, 20%, and so on. So they like to take the 10th of recall. That gives us 11 points, right? 11 points, 0, 10, all the way to 100. It's like the B+3 thing with the number of children and the number of keys. There's a +1. So this is why you get 11 and not just 10. So this is why it's called the 11-point interpolated average precision. And it's a simplification of the curve, basically, in this way. All right. And you no longer have these horizontal things in there. You're unlikely to still have horizontal parts, right? If you only look at this. Okay. So this is my awesome search engine. This is my poor search engine. And now that we have these curves, so in that case, I didn't backtrace horizontally. Now that we have these curves, what we can try to do is compute a metric out of this. So in order to compute a metric, we typically don't do it only on a single query, that was a single query, but we do it on many queries, right? Like this, you have plenty of queries, you draw plenty of curves, and on every query, you compute the average precision, right? You basically compute how much average precision you get. You can do it all the way to 100%, or you could also say, okay, now I stop at 50%, I stop at 10% of recall, right? But you basically compute the average precision on one query, and then like this, and then you compute the mean average precision, meaning that not only do you average for one query across the recalls, but you also average over multiple queries and information needs, right? So the name is kind of funny because mean and average is kind of meaning the same thing, but it's nicer than to say the mean precision or the average precision, right? So we call it the mean average precision or MAP, and that's it, right? So this is the formula right there. It's just basically a double average that you sum over all the precisions, and then you both average on the recalls and on the queries. Who understands that formula? What's going on here? It's just a double average, really. Okay. So this was one more thing, right? Now we have an actual metric that we can use on a ranked retrieval system. Now there's another thing that we can do. And again, it's based on a thought experiment. Imagine that I have some information need and a query that gave me these results. And I know that based on this information need, K documents are relevant. So of course, in practice, I don't know K, right? But assume I do know K. What I could do is click K times on the button next and get the top K, right? Exactly that same value as the actual number of relevant documents. If I'm super lucky, I'm going to get exactly the K relevant documents. If I'm less lucky, some of them, but not all of them. And now I'm going to consider the case that I do click next until I get as many documents as the actual relevant documents. And I'm asking the question, in that case, where am I on the curve, on the precision recall curve, when I'm actually stopping here at K documents? So when we do this, this is called the R precision. Who sees that if you do this, you have K relevant documents, you return the top K? Who sees that in that case, the precision and the recall are identical? Giving you a few seconds to see it. Who sees that these are the same, precision and recall? Raise your hands once you see it. Okay. It's exactly the same number, 4 or 4. You just move from the bottom left to the top right, but the ratio is the same. So this is the same precision as the recall. And that's an example of how we can have it. In that case, both the precision and the recall are 67, yes, I hear 67. So indeed, both the precision and the recall here are 67%. This number is called the R precision of my ranked retrieval system, right? The R precision. How do I get it from the curve? Well, I just take the intersection with y equal x, right? Just with this curve. I just take the intersection, and this is how I get my R precision. Who agrees with that? Right? It's kind of, if you think a few seconds, that kind of makes sense, because if you click K times on the button, you just go down and to the right until you reach this intersection, right? And then you know that you have exactly returned the same number of documents as the number of relevant documents. Okay, that is another metric. It's another metric of the system. And the higher the metric, so if you imagine now looking at this curve right there, so now we are here. Imagine that it's higher. What does it mean if it's higher? It means, let's say we would be here. In order to be here, it means that you basically came this way, right? If you're here, this is awesome because you came this way, right? If it's bad, and if you have a low R precision, it means that you got a lot of bad results and then ended up here, right? So the R precision is also a good metric. And again, the goal of this, whether it's the mean average precision or if it's the R precision, you just want to end up with one number. This is your goal. You want one number that says yes or no, the system is good or it's not good. So the map is one number. The R precision is also number for a specific query. And of course, you could also do it for multiple queries and take the mean R precision across multiple information needs and queries. Okay. Everybody following? Yeah? Okay. This should be a bit easier than the previous lecture that had a lot to digest. Okay. All right. Here's another one, yet another way of measuring things. Remember that I told you there's precision recall, and I also talked about specificity. Specificity is the dual of the recall. Just like the recall is among the relevant documents, which ones you return, the specificity is the opposite of that. It's like for the non-relevant documents, how much did you not return? This is the specificity. So now what I'm plotting here is on the x-axis, it's 1 minus specificity. It just means I'm taking the Spiegelung. I'm just mirroring this, right? So I start at 1 and end up with 0 of specificity. So this is what the 1 minus does. And on the y-axis, I'm actually plotting the recall, except that in that context, they don't call it recall, they call it sensitivity. But sensitivity is just another name for recall. All right. So if we plot this, what's going to happen? We get a curve like that. But let me explain what this is really about. ROC actually comes from electronics. I think, I might get it wrong, but I think that ROC means receiver operational characteristics or something like that. Maybe you could quickly Google our ROC. I think it's receiver operational characteristics. I'm just going to tell you a story. Imagine you're on the beach and you have a metal detector. You know, you're looking for it is receiver operational characteristics. Receiver operating, thank you, operating characteristics. Okay, so you're on the beach and you're looking for Bitcoins or whatever these days, and you just detect them with metal. And you have this beep, this instrument that is able to beep. And it has a little knob where you can just say how sensitive it is. So maybe you start with something that is not very sensitive at first, and you just walk on the beach and you just walk and nothing happens. It doesn't beep. So what do? You increase a little bit the sensitivity, right? You turn a little bit the knob, hoping that maybe it's going to beep now. And then indeed, at some point, it starts beeping, but it still doesn't beep often enough for you. So you start turning the knob more and more and more. But what's going to happen after a while if you continue turning the knob? Then it's going to beep the whole time. It's going to keep beeping. It's going to be very sensitive. And now it's beeping even when there is absolutely nothing, right? This is why, basically, when I turn the knob, I'm trying to go up. I'm trying to increase my recall. I want it to be more sensitive to metal. But when I do that, what's going to happen is that I lose specificity. At first, I'm super specific. It never ever beeps if there's nothing. But if you start turning the knob, it's going to start beeping for nothing. This is why you lose specificity. You start having false positives. So this is why you get a curve like this, if you would draw it. So in my example, it's a metal detector on the beach, but you can do exactly the same thing with a ranked search engine, in fact, right? So this is why it's called ROC, because of this electronics motivation, but and this is why it's called an ROC curve, but you can do the same. So this curve is actually also very insightful. learn from it. First, this is a very good curve, because in that case, I managed to increase the sensitivity, the recall, without losing too much specificity. So it means that I don't have so many false negatives, right? That would be lots of false negatives here. It means that it's not beeping enough. But in that case, I managed to make it beep and actually find things. But in addition to it, the reason why it's a good metal detector is that it doesn't beep for nothing. It doesn't have so many false positives. That would be getting a lot of false positives. It means that it moves to the right too early, right? So this is a good system if I put everything together. So the green zone is I like to go up, staying on the left, and then stay up. I don't want to go to the right too early, right? So this is the sweet spot. An ideal system would go all the way to 100% recall and still 100% specificity. So it would be on the top left. In practice, it's a bit less than that, but that's it. If you have a system that would be there, that's not ideal because it keeps beeping for nothing and it never ever beeps when there is something. Would you buy that metal detector that keeps beeping when there is nothing and it doesn't beep when there is something? Of course you would buy it, right? That's perfect. You just wait until it doesn't beep. And indeed, it means that this is a fine search engine. This is an awesome search engine. This seems to be a bad search engine, but this is actually a great one because again, you just invert the outputs and you just, you can still use it. So this will actually find things. So this is actually an awesome search engine also. What you really don't like is this. This is awful. This is just noise. It just keeps beeping randomly and there is no correlation whatsoever with actual metal, right? Okay. So this is it. This is a really, really bad search engine. Okay. Now, I don't know why I'm throwing that at you. It's also something mentioned by the book, but luckily this is not a machine learning lecture, so I don't actually have to explain this, but there are many other ways that you can quantify and find metrics based on what you look for. You probably see that it's close in spirit to the map metric, computing a mean and so on, but it's just coming from machine learning motivations, right? But just to show you that you can also come up with more metrics in that case. Here it's 2 to the power of PQK. Again, compare it to the map formula. Where is the map formula? Here, right? So you still average over Q. You still compute based on the curve, the precision for Q and K. So the Q is the query and K is the where you are in terms of recall. And here is just a modified formula. Where is it? Yes, here. What is interesting here, coming back, let me give you a bigger picture on this. Last week, when we talked about the weights that you have in your scoring system in the vector space model, I showed you by default it's TF-IDF, but you have this whole menu with the starters, main dish, and dessert. And you can code it with letters. And then I threw formulas at you. I said, okay, N means this, and A means this, and B means this. And probably that felt very artificial. Like, why exactly this? Why does A mean exactly this formula here that I threw at you? Well, in fact, all of these formulas, they have a motivation somewhere. There is somewhere a paper in which people took an approach and computing things in a way with a certain motivation. And then they ended up with these weights. And because of that, that was integrated in existing systems as a way to control weights. So these weights, they don't fall from the sky arbitrarily, they actually come from some motivation. And in that case, this could be considered, just like in the smart notation, an alternate way of computing map. Instead of PQK, you have 2 to the power of QK minus 1 divided by 1 plus K. Why? Because there is a whole paper explaining that if you use machine learning and solve it and do maybe, I don't know, some stochastic gradient descent, I'm just making that up, and then you end up with this. Then that gives you a motivation for using a formula off the shelf. Okay, this is going to keep happening again, because I can maybe give you a small, let's hope no, I can do that. It's not going to be a spoiler. Next week and the week after that, we are going to look into probabilistic information retrieval, and then we are going to look into language models. And what's going to happen is that with a completely different story, a completely different approach, we are in fact going to end up with formulas that correspond to the smart notation menu just by magic. And this is actually where they came from, because with an alternate approach, you find this. So that's what we'll do next week. Okay. So just this as a parenthesis to show you that there is many, many different metrics that you can have. Okay. Now, the metrics that I gave to you, these are only metrics for the quality of the system in terms of returning relevant results. But in reality, you might have other considerations than whether it's correct or not, because if you have a computer that correctly outputs 22, but it takes millions of years to do that, that computer might not be very useful, right? So you also might want to care about the speed of search, how quickly the results are returned. That would be performance. That's a measure of performance. You might also want to care about the speed of the index construction. So this is when you run your construction. So typically for a search engine 2 days, there's 48 hours until a new page makes it into the index. And probably that's an evolving number, but last time I checked, it was 48 hours. That also matters. 48 hours is probably a sweet spot. Maybe 1 week or a month would be too much. Less than that might not be necessarily useful for most people. Another measure you want to care about is the expressiveness of the query language, the Boolean query system, the phrase search, the quotes, and so on. In fact, if you look at a real search engine that you find on the internet, the query language is a mix of all of that. It tries to interpret that as a Boolean query, as a phrase query. You can mix and match, and it typically goes through all the indices and then mixes the results together, computing scores. So the expressiveness of the query language is also part of the user experience that you have there. So most users, when they type a query, they just type a sentence or copy paste an error message, but there also are power users who know about all the tweaks. For example, you can also, in a Google search, you can also restrict to the date or to the type of file you want, or you can restrict to the domain that you're looking for, right? So this is part also of the system. And finally, you care about scalability. You also care about whether the system that might have a very good evaluation is scalable. Because if you make it work on a collection of 1,000 books or 1,000,000 books, but then it breaks at 1 billion or at 1 trillion books, then that doesn't work anymore. And here, that's the whole week we spent on the index construction that is relevant. So you see these metrics, there's many different dimensions that always depends on the use case of what you are looking at. Okay, this actually concludes the lecture on evaluation. In fact, that doesn't only conclude this; it concludes the whole part of information retrieval that is taught at the bachelor's level. So we are done with the bachelor's level. Congratulations, that's it. Now we are going to spend the remainder of the semester on master's level. Wow. Probabilistic information retrieval language model. So we are going to get into the advanced part. But the bachelor's level, it's over. We did it. So what I can do now, I have two possibilities. It's 10 to 12. I can either call it a day for you, or I can already start with the probabilistic information retrieval. I actually just start with some 101 of probabilities to refresh. So let's vote on that. Let's make a vote. Who wants to stop the lecture now? You've had enough for today. Let's stop on evaluation. Let's go celebrate the bachelor's level of this. Who wants to stop here? Please raise your hands. 6, 7, 8, 9, 11, 12, 13, and on Zoom. 13 in the lecture hall on Zoom. Everybody wants to stay on Zoom? Okay. Who wants to already start now with probabilistic information retrieval? 1, 2, 3, 3, 4. Okay, how many on Zoom wants to continue? Nobody? +1? Somebody wants to continue? So we are at 5. Any last word? It's 13 against 5 for now. Okay, so it seems the majority wins. This is Swiss democracy. So that's it. Go celebrate, and I'll see you next week with the probabilistic information retrieval. It's really, really awesome. We're going to write a lot of formulas. I'm going to try to not scare you too much with that, but be prepared to see a lot of math. So thank you very much, everybody. Enjoy the exercise session, and I'll see you next week. Thank you very much.